So this is a continuation of Chapter 2 lecture notes. I received a question. Somebody asked, how do we know the coordinates of the terminal point for terminal number equals pi-4? And that's a very good question. So if you go to the class website, you'll notice, I believe, I'm trying to paste a picture into the whiteboard. Seems to be struggling a bit. It didn't want to take. Okay, let me try again. So let me delete this page and try again. And let me go to the website and pull up the picture since this tool isn't allowing me to cut and paste. 1 second. So I'll go print screen. And it's that circle figure that's near the top of the class web page, which I'm trying to paste. So let me cut it and paste it. Okay, I guess I better give this lecture a title too as well before I get started. So this is Chapter 2 continued, and we're going to be talking about graphing trigonometric functions. Okay, all right, now, so go back to the question I originally stated. Somebody asked, what are the coordinates of the terminal point for t equals pi-4? And I just pasted a figure here, and this figure is available on the class website. Now, this, of course, this circle is the unit circle. So the coordinates of this point are 1, 0, and the coordinates of this point are 0, 1, and the coordinates of this point are negative 1, 0, and the coordinates of this point are at 0, negative 1. Okay, so those are the 4 distinct points on the unit circle. And of course, you know the equation of the unit circle centered at the origin is x squared plus y squared is equal to 1. Okay, and all right, so what t is, okay, t is your terminal number. All right, and on the unit circle, that's the distance on the perimeter of the unit circle from the point 1, 0. So this is your terminal number. All right, and so pi-6 is, for t equals pi-6, that means that it's this arc length distance from t equals 0. Okay, so the arc length distance that I've accentuated in red is pi-6 radians. Now, what does this 30 degrees mean? Well, the 30 degrees is this angle, and we call this the subtending angle for t equals pi-6 on the unit circle. So this is the angle subtended by t equals pi-6. All right, so, and that works for the unit circle. Okay, now for 45 degrees, well, okay, so we know that if we look here at the point negative 1, 0, we see that 180 degrees is equal to pi radians. So if we come here now and we plug in 180 degrees for pi, well, that 180 divided by 4 is 45 degrees. So that's a 45 degree angle that subtends t equals pi-4 radians on the unit circle. Right, so, and as we know from algebra, a 45 degree line is, the equation of a 45 degree line is simply y equals x. Okay? So that black line that I've accentuated, that line's equation is y equals x. Now, what we want to know is we want to know the coordinates of the terminal point that I've accentuated in green right here for t equals pi-4. So all we have to do is make use of the equation of the unit circle, which, as you know, is x squared plus y squared. And since the line y equals x, where it intersects the unit circle would be the terminal point for t equals pi fourths, right here, as shown, okay? So all we do is say we plug in x for y, and we have x squared plus y squared. I'm sorry, x squared plus x squared. I'm plugging in x for y, okay? So that would be x squared plus x squared is equal to 1. So we have 2x squared is equal to 1. And so x squared is equal to 1/2. And then we take the square root of both sides. And so we have x is equal to plus or minus 1 over the square root of 2. And if we decide to rationalize this number, that would be plus or minus the square root of 2 over 2. Now, since we are in the first quadrant for t equals pi fourths, the terminal point coordinates have to both be positive. So that means we take, for t equals pi fourths, okay, the reference number, which we discussed last lecture, is t bar is equal to pi fourths, and its terminal point, which I'll call TP, terminal point, its coordinates with the square root of 2 over 2 for the abscissa, and since the ordinate is equal to the abscissa, the square root of 2 over 2. Okay. Now, and then, okay, so suppose you want to find the terminal point for 3 pi over 4. Well, you use the symmetric properties of the circle, and you note that the ordinate for 3 pi over 4 will be the same as the ordinate for the terminal point for pi over 4. And the abscissa for 3 pi over 4's terminal point is the negative of the abscissa of the terminal point for pi fourths. And then you can use symmetry to calculate the coordinates of the terminal point for 5 pi over 4, and then you can use symmetry to calculate the coordinates of the terminal point for 7 pi over 4, knowing that this is a perfect square inscribed in a unit circle. So you can proceed that way. So just to clear up any confusion. So now the terminal number on the unit circle, not sure if I emphasized this clearly enough last lecture, but it's the length. It's maybe considered the arc length. So in this case, the blue arc length is pi halves radians, and so on and so forth. All right. So, and then last lecture, of course, we discussed the graphs for the sine function and the cosine function, and how we map the terminal numbers, the coordinates, the coordinates of the terminal points onto the xy axis. So we know that the abscissa of the terminal points correspond to the cosine function, and the ordinates of the terminal points correspond to the sine function. Now the other remaining four trigonometric functions, which are tangent, cotangent, secant, and cosecant, those are all rational functions, and those require special considerations. So before we proceed to do that, what I want to point you out to is the lecture notes on Chapter 1. And in class and in Chapter 1 lecture notes and video, we talked about graphical transformations, such as vertical shrink, vertical stretch, vertical shift, and the corresponding operations on the horizontal shifting or horizontal transformations of graphs. Okay, so let's talk about how that proceeds. So let me pull up a graphical editor. So I'll paste insert an internet browser, and let me configure. We'll start off with, say, the cosine function. So let me configure this graphical browser to portray the graph of the y equals cosine x. So 1 second. Takes a little bit of work to do this. So, and this calculator is available on the class website, so you can do the same thing on your own as that I'm doing here in the video by using the resources on the class website. All right. Page not found. Is it not found? Why not? Desmos.com. Oh. Okay, there we go. So let's configure the properties of the coordinate system to show labels, show grid lines, show axis. Yes, of course. And in the window, how about we portray the window in radians? And for the x-axis labels, we'll label the x-axis in terms of multiples of pi. Right? So this will be a standard representation of when we graph trigonometric functions to represent the x-axis in terms of values of pi. All right. So what you might want to do is you might want to try and say print out this particular coordinate system where the x-axis is marked off in multiples of pi, and you can use this as practice drawings before you attempt to answer questions through the internet. Okay, so let's start off with y equals cosine of x. Will that work? The flat line on it. I think I may have fat fingered something here. Let's try it again. Y is equal to cosine x. So why is it? Yeah, sometimes x kind of tricky here. Let me check the window settings. So this radians. Oh, there we go. Yeah, okay. Yeah, so you have to make sure that you check the radians box. Okay, right here you have a choice for the window setting of radians and degrees, just like on your calculator. And if you check degrees, you see you get this flat line, which is no use to you. Make sure that you check radians so that you can get the x-axis, the numbers on the x-axis are interpreted as terminal numbers, and then the outputs are interpreted as a cosine of a terminal number expressed in radians. Okay, and you'll need to configure your calculators that way as well. All right, so the blue curve is y equals cosine x. Now, notice the periodicity of the cosine function. So let me annotate some of the periodic notions. So if we start at t equals 0, terminal number 0, and we go to terminal number 2 pi, okay, this denotes 1 period. So maybe I can accentuate it. Let's see here. I go here, and let's say y is equal to cosine x, where x is, say, between 0 less than or equal to x less than or equal to 2 pi, right? And so the green piece, zoom out a bit, is 1 period. Okay, so green over on blue is kind of hard to see, I understand. But the green is 1 period, so we can say construct another period, say from negative 2 pi to 0. So y is equal to cosine x from negative 2 pi less than or equal to x less than or equal to 0. And so now the purple would be a second period. So if we zoom out, you'll see the purple and the green are 2 periods. And if you zoom out even further, you'll see the periodicity manifests itself for the cosine function. It just oscillates. This is called an oscillation. And note the range of the cosine function. It never goes above 1, and it never goes below negative 1. Okay, so that's the range of the cosine function. You see, the peak value, this is, as we discussed from chapter 1, we have a local maximum at t or x, whatever variable you choose to call it, a local maximum at t equals 1. And why is it a local maximum? Because as you approach t equals 0 or x equals 0 from this direction, you'll see that it's an increasing function. As t increases, the output of the cosine function correspondingly increases. And then once you get to the left of, to the right of t equals 0, you start going in this direction. Okay. For increasing values of t, the function decreases all the way to t equals pi. So the cosine function is decreasing on this interval, right? And so when you have this transition at t equals 0 from increasing to decreasing, that of course is considered a local maximum, right? And that's from chapter 1. And then you can see the local minimum occurs at t equals pi, as well as odd multiples of pi. So if you look at odd multiples of pi, so like right here is 3 pi, you'll see that the local minimum of the cosine function occurs at odd multiples, like negative pi is an odd multiple of pi, pi is an odd multiple of pi, 3 pi is an odd multiple of pi, and then all the local maximums occur at even multiples of pi. So negative 2 pi, 0, 2 pi, those are all even multiples of pi. So that's the cosine function. And I'm assuming that you understand how to translate the abscisses of the terminal points on the unit circle onto this flat rectangular representation of the cosine function. Okay, so enough said there. So we get back on task here. Now, of course, we can do things like we can transform this function like we did with the algebraic functions from the first lecture. So for instance, suppose we want to shift the cosine function up 2 units. So to do that, to accomplish such a thing, we would, of course, do as we do in algebra. We would add 2 to the output. So add 2 to the original function. And then now it's shown in orange is, okay, so I'll get rid of these period displays. Let me put back the original function. So the original function, cosine function, is now shown in black. Sorry. All right, so compare. You can see the black curve is y equals cosine x, and the orange curve is the cosine function. All the locus of points that make up the cosine function all shifted by 2 units vertically. Okay, and then now that is an example of a vertical shift. We can an example of a reflection is if we took the original function y equals cosine x and we multiplied it by -1. So this will reflect the cosine function about the x-axis, and that is shown in red. All right, so let me get rid of the orange curve, and you can see the red curve is basically you take the black curve and you flip it about the x-axis, and you get this. See how that works? And by the way, this is not the sine function. Okay, the sine function you can tell because the sine of 0 is 0, and in this case, the output here is what? 0, -1. Okay, all right. Okay, so that's another transformation. And then we had also discussed the idea of a vertical stretch. Okay, so if I were to say multiply the original function by, say, 3. Okay, so 3, that would stretch all of the outputs by 3. So you can contrast now the red curve with the original black curve, and you can see how the function is stretched vertically. And so another terminology that we'll talk about shortly is this distance from the x-axis to the local max right here. Okay, that's called the amplitude. And so when you multiply the cosine function or the sine or any trigonometric function by a number, like in this case 3, that's your amplitude. Okay? And then, of course, we know about period. So in this case, the period can be considered the fact that where the curve starts repeating itself in the outputs. So you see you have from negative 2 pi to 0, you have a set of distinct one-to-one outputs. But once you start going past 0, your outputs start repeating themselves. You reuse outputs that you had used prior. And so the period then is this distance along the t-axis or x-axis where the outputs of the function are distinct. Okay? They're unique for each value of t. And once you spill over past this interval, the outputs start duplicating themselves. So in this case, the period is 2 pi, the amplitude is 3. So those are some terminologies we'll need to know for trigonometric functions. All right? Okay, so I hope this is clear to you. If it's not clear, please send me an email to ask questions. All right, so this is a vertical stretch. Now, of course, a vertical shrink would be if we multiplied the original function not by a number greater than 1, but say by a number less than 1, say 0.5. Okay, so that will compress the curve. As you can see now, the red curve has a smaller amplitude than the original black curve. Okay, but the intercepts, the x-intercepts remain the same. The x-intercepts remain the same. The y-intercept changes. Okay, obviously. So the y-intercept changes. It's now a half instead of 1, and intercepts change the same, and then the amplitude, of course, becomes smaller. So this is a vertical shrink. Okay. Now, we can do a reflection combined with a vertical shrink. So, and that would be, say, if we multiplied the original function by a number between 0 and 1. Okay, and then we'll readily see that we have a reflection about the x-axis or t-axis, and then a vertical shrink. All right. Okay, so that's how, and you can do this for any of the trig functions. Okay, you can do this for the sine, all of the trigonometric functions. So that's the vertical. Let me see what else. Oh, okay, so one note, the amplitude. So let's consider this red curve. Even though we multiplied it by -5, the amplitude is still essentially the absolute value of this coefficient. So, for instance, let me clarify. So if I have y is equal to a cosine x, like this. So the amplitude is the absolute value of a. All right, so note that. Okay, now let's talk about horizontal stretching. Okay, that's an interesting topic for trigonometric functions. So let me get rid of this red curve. We'll go back to the original black curve. Now, a horizontal stretch is achieved the same way as we did with algebraic functions. That is, we modify the argument to the cosine function by multiplying it by some number. And some interesting results happen. So for instance, what if we were to take the x value, the argument, and multiply it by 2? What would the effect be on the graph? Would it horizontally stretch it, or would it horizontally shrink it? Okay. If we were to multiply it by 2, it's basically a compression. So let's verify that. So let's graph y is equal to cosine of 2x. Right, and that'll be shown in blue. Okay, so the blue curve, you can see, is the black curve squashed in the x direction. Right, so let's zoom in a bit and see what the implications are. Right, and How about I restrict the blue curve to, say, between 0 and 2 pi, right? So let's make for visualization purposes. So we'll go 0 less than or equal to x less than or equal to 2 pi. All right. And we'll zoom to that or pan to it. Okay. All right, so let's just focus on the interval 0 to 2 pi. Now, the black curve has one period, 0 to 2 pi. In other words, it goes through the distinct outputs of the cosine range from 0 to 2 pi, and then it starts repeating itself. But look what's happened to the blue curve. The amplitude is not modified. The amplitude of both the blue and the black curves is still 1. Can you see that? See, it's from the x-axis to the peak value, and that's still 1. We can, I think there's an identify tool here. Yeah, see pi 1, so we're still at the local maximum. But what's interesting is that the period of the blue curve has now changed. The blue curve cycles through its range of outputs for the cosine function twice in 2 pi. So let me accentuate one period of the blue curve in red. Okay, so we go, so notice that as I trace along the blue curve, I'm going through all the range of values from 1 to -1 and then back to 1. So the red curve shows all of the outputs that the cosine function can attain from -1 to 1. All right, so how many periods of the blue curve are there between 0 and 2 pi? Well, there are 2 periods, okay, because now we have this other piece between 0 and 2 pi. So what we've done, the takeaway here is that when we multiply the argument to the cosine function by a number greater than 1, okay, the effect is, or at least insofar as we've multiplied the argument to the cosine function by a integer number greater than 1, the effect has been to compress the curve. So in the case of 2, we've doubled our period. Okay, so there's a formula here. The formula is the period of a function. Okay, that is the distance for one complete cycle of the curves. And by cycle, I mean the cycle is the interval on the t-axis where the function ranges from goes through its full range of outputs. Okay, so perhaps I should write that down. So a cycle is an interval on the t-axis, the terminal number axis, where the function takes on all outputs Oops, I can't write there. Takes on all outputs of its range. So the cycle of the standard cosine function and the standard sine function, as well as the secant and cosecant functions, is 2 pi. That's the length of a cycle. All right, now, and the cycle is often called period. So cycle, period, those two words are used interchangeably. So now, if we multiply the argument by 2 pi, then the cycle length, or the period, is now pi, right? And so the formula is the period, so the period for sine, cosine, secant, and cosecant, there's a formula, and you should probably memorize this and understand it as well, of course. It's 2 pi over k. Okay, and what is k? So if we were to write y is equal to cosine kx. Okay, the period is 2 pi over k. And the assumption is that k is greater than 0. Okay, k is greater than 0. And we don't have too much to worry about because the cosine function is an even function. So, but we have to be careful with the sine function as well as the other. So, so the period of the sine, cosine, secant, and cosecant is the interval 0, 2 pi over k. All right, so that's the period. And so in the case of y equals cosine 2x, k is equal to 2, so 2 pi over 2 is pi. Okay, all right. So that's a horizontal shrink of the cosine function. So what if we say 1/2? So that would obviously make it a horizontal stretch. All right, so we can, next curve, I guess I can do a horizontal stretch. We can contrast the 3 modes here. So how about y is equal to it'll let me type. Hello. I have to wait on the internet to catch up. So y is equal to cosine 0.5x. So this would be a horizontal stretch. And I'll just let it run. And let's see what the green curve then would be your horizontal stretch. And let's see what that looks like. So I'll have to zoom out a bit, right? And so we anticipate the period to be 4 pi. All right, so let's verify the fact that the period of this curve now is 4 pi. So trace, okay, trace, I'll use a pen tool to trace. I'll trace in, say, purple, where the green curve goes through the full range of outputs. All right, so 1 is the output at t equals 0. Then when we get to 2 pi, the output is -1. And then we start going back toward 1 again. And so when we get to 1, the output of 1, we stop because we've gone through the full range of outputs. Then we just start duplicating out previously used outputs. So you can see the purple trace, it's 0 to 4 pi. Okay, all right. And you can do the same things with the sine function. You can horizontally stretch, horizontally shrink, and then of course you can combine the two. So how about we do that? So let's consider the graph where we combine the two. So let's see. Checking the notes here, making sure I've got everything. Okay, yeah. So let's go back and we've used cosine quite a bit, so let's practice using the sine function. So I'll get rid of these and erase the purple. And so let's practice with the sine. So y is equal to sine x. Okay, shown in blue. And so suppose we want to do a horizontal stretch of the sine function. So if we do y is equal to sine, now to do a horizontal stretch, we have to, the k value has to be between 0 and 1. So say x over 2. All right, so you can see the orange curve is a horizontal stretch of the original sine function. See how it's stretched out? Now we can combine horizontal stretching with, say, vertical stretching. So how about y is equal to, say, maybe 4 times sine x over 2. So we combine transformations here. and that's shown in black. So let's see what the combination of transformations. Okay, so we had a horizontal stretch culminating in the orange curve, and then we had a vertical stretch culminating in the black curve. So even though we stretched the orange curve vertically, its period is still 4 pi, as you can see. Right? So its local max is pi force right there. Okay. Now, what happens? Now we can still do some more transformations. We can take the black curve, for instance, and we can reflect it about the t-axis. So how about y is equal to -4 sine x over 2. Okay, and that's shown in red here. Now, what's interesting is the way in which I got the graph of the red curve. I proceeded in steps, okay? And this is how you would do it if you were to do this using paper and pencil. If you were to take the graph paper and I asked you to sketch y equals -4 sine x over 2, you would start off by sketching the graph of y equals sine x, right? Probably on one period, 0 to 2 pi. Then you would next proceed to do y equals sine x over 2 by doing the horizontal stretch, okay? Knowing that you can just use the reference points 0, t equals 0, t equals pi, t equals 2 pi, 3 pi, and so on. And then possibly, if you want to get more sophisticated, you can use the reference points at pi halves, okay? And then you can kind of gauge the graph that way. And then, okay, and then the third step you would do would be to multiply the output by 4, shown in the black curve. In other words, modify the amplitude to 4. And then finally, you would do the translation about the t-axis in the red curve. So the way I did it here is the way you would do it using paper and pencil. All right, so examples of that. And you can do these operations can be done with all six of the trigonometric functions, and I'll have some more for you. Okay. All right. What next? Okay. Now, so we've done transformations that involved shifting, horizontal shifting. No, not yet. That's the next thing we want to do. But we've done horizontal stretching, horizontal shrinking, vertical stretching, vertical shrinking. So now the next thing we can do is we can shift the sine and cosine functions. So pull up another page, and I'll post a technical note for you. Let me pull it from the lecture notes. If I can find it. Okay, so let's talk about shifting the functions. And it's done the same way as we did with algebra. Okay, so, and I'll paste it here. Let me prepare it here. So, and this may be in the book, I'm not sure, this technical note. So shifted sine and cosine curves. Just like with algebraic functions, to shift the function, you add or subtract this number b from the argument x, okay? And so, of course, if you subtract a number from the argument, that is a right shift. If I were to add a number to the argument, that would result in a left shift. So in this case, look at this notation here. So this equation, you have an amplitude, which is the absolute value of a. You have a period now, which is 2 pi over k, and now you have a right shift b. And the technical definition is b is called a phase shift. Okay, we're shifting the terminal number, or we're shifting the angle. And so when normally, if you don't do a shift, the period is here, is on this interval. This defines one period of the sine or cosine or secant or cosecant function. Now, if we were to shift the graph, say, b units to the right, okay, what you would have to do is you would have to add you would have to add b to the endpoints of the interval. Okay, so yeah, so these are the endpoints of the interval of a period. Okay, endpoints. These aren't the coordinates of a point. These are the endpoints of the period of an interval. So when you shift the interval b units to the right, you have to add b to the endpoints. And if you shifted it to the left, okay, then you would have to subtract b. Well, you could. You don't necessarily have to because of periodicity, but you could subtract b from the endpoints of the interval. And so this would define the endpoints on your t-axis. So you would have your t-axis, or you could call it x. Then you would have b, negative b here, and then you would have negative b plus 2 pi for a left shift, right? 2 pi over k, excuse me, like that. So that's how that works. All right, so I can show you an example. Let's see, let me find one that's in the book for you. Okay, yeah, so yeah, here's a good one. I found a good example. So let me go back to the graph. All right, and so let's combine, let's graph a sine function that has a combination of an amplitude, a modified period, and a right shift. So how about, let's discuss the components here. So y is equal to 3 times sine of 2 times x minus pi over 4. Is it not drawing the graph? Okay, there it is. Okay, so there's a sketch of the graph. Now, let's zoom in. How about I do it over, okay. So suppose we want to explore this curve on one period. So what it would be the start of the period of this graph? Well, we know that for reference, for perspective, how about I just go ahead and plot y equals sine x? Okay, and that's shown in blue. So we're comparing the fundamental sine function shown in blue with this modified sine function. It has a modified amplitude, period, and phase shift of pi 4. So the start of the period let's talk about the red curve. So we want to know what the start of the period is. All right. The way you would determine where it starts is, we know that the sine function's period starts at 0. So the start of the period for the red function, the red curve, would be found by setting 2 times x minus pi over 4 equal to 0. Okay? And solving for x. So when we solve for x, that would be, let's see here. That would be x is equal to, what, pi halves. So in this case, the period starts at pi halves. So let me set the window properties so that we're in radian mode, and the x-axis is, the x or t-axis is represented in multiples of pi. Can I get away with that? All right, so let's see if that worked. Didn't work. Let's see, window settings. Come on, window settings. So in radians. There we go. Okay, so now we got it. All right, so the blue curve, no, excuse me, the red curve's period starts at pi halves. That's the first x-intercept, essentially. That's where the x-intercept is. No, I'm sorry, not for this particular curve. So we start the period of the red curve at pi halves. Is that right? Let me check. Pi halves. No, I'm sorry. I made an algebraic mistake, right? I beg your pardon. I forgot my 2. I'm making the same mistakes my students make. Okay, so 2x is equal to pi halves. So x is equal to pi fourths. That would be the start of the period. Yeah, so the period would have to start at the x-intercept. So right there. Okay. Yeah, I thought something was kind of strange there. It's self-correcting. So pi fourths 0. So that's the start of the period right there. Okay. And so the end of the period would occur by setting the argument to the sine function equal to 2 pi. Okay, so if this thing will let me scroll, okay, so we say 2x, 2 times x minus pi fourths is equal to 2 pi, and we solve for x. So we have pi minus pi fourths is equal to, no, I'm sorry, x minus pi fourths. What am I doing? I'm having a bad day today. That would be x minus pi fourths is equal to pi. And so solving for x, the end of the period would be 5 pi over 4. Right? So the period of the red curve would happen on the interval pi fourths to 5 pi over 4. So that's one period. Okay? And so that's where this function transitions through its complete range of values. So where is 5 pi over 4? Let's zoom out. That would be right here. Would it not be? Let's check. Yeah, right there. Okay, so I've annotated the period. See how it transitions to its full range of values before it starts repeating again? You may be tempted to say, oh, well, here's the period. But if you say 3 pi over 4 is the endpoint of the period, well, you've omitted all of these values of the function below the t-axis. So be careful that you make sure that it goes through its full range of output values. All right. So this is a shifted sine function, shifted to the right because we subtracted pi fourths from its argument. Okay. What else? So we can see the effects of shifting left and right. All right. So how about we take the sine function and we shift it left now, say by pi thirds. So how about y is equal to sine x minus, or plus rather, this would be a left shift, pi over 3. So as shown in green, okay, as shown in green, the green curve is now the blue curve shifted to the left pi thirds. So what would be the period of the green curve? All right, so as before, we set the start of the period would be found by setting x plus pi thirds equal to 0. Okay, so the start of the period then would be negative pi thirds. And the end of the period would be found by setting x plus pi thirds equal to 2 pi. Okay, and so that would be, what, 5 pi over 3? Okay, and since we didn't do a horizontal stretch or shrink, the period is 2 pi. Okay, so let's say we identify this point. So there's negative pi thirds, the start of the period. and we have to go through the full range. And so the end of the period would be here, 5 pi over 3 for the green curve. Okay, and then we have 3 x-intercepts along the period. Okay, all right, so that's how that works. So we can find the amplitude, the period, and phase shift of a trig function. Let's see here. This diagram, this next problem would be worth, I think, useful to talk about. So let me pull it up from the lecture notes. Let's work in another example. All right, so I guess, yeah, let me print that, the solution here, so we can talk about it. Okay, so the question is this. We want to find the amplitude period and phase shift for, and here's the function, y is equal to 3/4 cosine of 2x plus 2 pi over 3. Okay, so to do this calculation, you have to reformulate the expression in terms of a standard form for the representation of trigonometric functions, and we have to format it like this. So y is equal to a cosine times k times x minus b. All right, so you have to express that. And so in this equation, it's not stood up that way. We have to basically factor out a 2. We have to isolate the coefficient of x so that we can get the period and the phase shift. All right, so if we were to do that for this problem, in this case, a is 3/4, and we would have to factor out the coefficient on x. So in doing so, that would be 2. Okay, so if we factor out a 2 from the number from the parameters in parentheses, that would be x plus pi thirds. Okay, because note that you can use the distributive principle to multiply each term in parentheses by 2 to get back the original equation. So we factored out 2. Now we also need to convert this addition to a subtraction, and the only way you can do that is if you go minus minus. Okay, so the conversion then would be 3/4 cosine 2 times x minus a minus pi thirds, because this is a left shift. Okay, all right, so transform it thusly, and so the amplitude, which I'll just call amp, is equal to the absolute value of 3/4. Now if it were negative 3/4, you would take the absolute value of negative 3/4, which, okay, so in this case it's just 3/4. And let's see, the period, as we discussed earlier, is 2 pi over k. which is equal to pi, because k is 2. And then the phase shift, which I'll call PS, phase shift, that would equal to B, which is negative pi thirds. So it's a left shift. Right? And this would be the picture right here. So amplitude 3/4. Here's the sketch. Well, first of all, here's the sketch. The blue curve is a sketch over one period of 3/4 cosine 2 pi plus 2 pi over 3. So the period is length pi. So you can see, we can check that 2 pi. So the distance from negative pi thirds to 2 pi over 3 is pi. I guess we can say, what is the start of the period? How do we know that the period starts at negative pi over 3? Okay, so that's something that this problem doesn't express. So the start of the period would again be found by setting the argument equal to 0. So we have 2x plus 2 pi over 3 is equal to 0. Okay, and so 2x is equal to negative 2 pi over 3. And so x is equal to negative pi over 3. So that would be the start as shown in this graph. That's how we knew to start at negative pi over 3. And then, of course, the end of the period would be found just by adding pi to negative pi over 3 to get 2 pi over 3. Or you could just run the calculation and do an end. If you need convincing, you can also say 2x plus 2 pi over 3 is equal to 2 pi. Okay, you can solve this. So 2x is equal to 4 pi over 3. And so x, the end of the period, would be 2 pi over 3. Okay. All right, so that's the interval for one period. We had a phase shift of pi thirds. So pi thirds to the left. All right, and notice what the phase shift did. It moved the x-intercept to negative pi 12. Okay, it moved one of the x-intercepts to negative pi 12. So how do we know that? How do we know that those are the coordinates of the x-intercept? That's another question. All right, so let me extend the page and we can derive that. Well, I'll note that the first x-intercept of the cosine function, let's revisit the cosine, consider the cosine function again, just at sketch. And so, or we can use the table. The cosine function over one period looks like this. Okay, so here's 2 pi. Okay, here's negative 1. Here's 1. And so here is the x-intercept. All right. So the x-intercept occurs at t equals pi halves. Okay, t equals pi halves. Okay, and this, of course, is t equals pi right here. And then we have another x-intercept at t equals 3 pi over 2. All right, now, since we take this curve, the black curve, and we have shifted it pi thirds to the left, that means the x-intercept, which I'll call xi stands for intercept, would be found by taking the original x-intercept, which was pi halves, and we subtract pi thirds. Okay, and when you do the subtraction, that would be what? Oh, is that right? We did a phase shift, so we took pi halves. Yeah, so that would be, let me think here. Amplitude. We did a phase shift of pi thirds, so is that the, oh, let's see here. hang on, let me check. Let me check that result. Phase shift. So we take the outputs. Oh, that's not right. How do we know the x-intercept here? Or can we know it? Oh, let's see here. That's not quite correct. We took the black curve and we shifted it pi thirds, so this point would shift here somewhere. It would wind up here, wouldn't it? Is that right? Let me think. Pi, so 2 pi over 3. That's strange. Oh, because, oh, I see what the error is. We're not shifting cosine x, we're shifting cosine of, no. The problem here is that this period is wrong. Okay, I see what the problem is. This pi halves is not the x-intercept. Sorry, I have the wrong curve. Thought that was, erase this. That's not right. No. Remember what we did was this curve involved a horizontal shrink. Okay, and so we the period is now pi. It's not 2 pi. So let me redraw the cosine function with a period of pi. All right. So sorry about that. So all right. So again, sketch the cosine function. Okay, and since we did a horizontal shrink, the period is pi. Okay, and so this is pi halves. All right, and then this would be what's the midpoint between 1.5? So that would be 3/4, right? So this would be 3 pi over 4 right there. Would be one x-intercept happening at, yeah. So this is cosine of 2t before we do the shift. Okay. All right, and then this would be pi over 4 right here. So the t-intercept is at pi over 4, and of course this is t equals 0. So now what we do is we subtract pi thirds from pi 4. So we take this black curve and we shift it to the left pi thirds units. And so that basically will take this x-intercept and it will move it to the left of the y-axis. Right, and so this coordinate is found by saying pi fourths minus pi thirds. Okay, and so that would equal to negative pi 12, as shown in the graph. So that's where the x-intercept comes from. Okay, it was found this way, the way I just did it. And then the other x-intercept, 5 pi over 12, well, that was found by subtracting pi thirds from 3 pi over 4, because the x-intercepts will shift to the left. Okay, so, and then of course the y-intercepts will change as well. That would be a different issue. We would have to probably wait until chapter 4 to compute the coordinates of this y-intercept. But as you know, the y-intercept would be, well, let's see, maybe we can do it. What would the y-intercept of the curve be? Well, it's found by setting x equals to 0 in the original equation. So the equation is y is equal to 3/4 times cosine 2x plus 2 pi over 3. And we're chasing the x-intercept, so we evaluate that at x equals 0. And so we get 3/4 times cosine of 2 pi over 3. Okay, and so what is the cosine of 2 pi over 3? All right, so one way is, I think you can look here. 2 pi over 3 is right here. And so what is the, you have to find out what is the abscissa of terminal number 2 pi over 3, of terminal point 2 pi over, the terminal point for t equals 2 pi over 3. So we know, all right, so here's how you would reason through that. Let's see, go back. Here's how you would reason through that. Okay, so what is 3/4 cosine 2 pi? All right, so we know that the cosine of pi thirds is the terminal point for so what is the terminal point for 2 pi over 3 radians? Okay, so from the previous lecture, we know that the terminal point for pi thirds, okay, we proved that, and I asked you to memorize that. It's 1/2 square root of 3 over 2. Okay, so that's for pi thirds. Now, since 2 pi thirds is a reflection of pi thirds about the y-axis, okay, the terminal point for 2 pi over 3 is when you reflect a point about the y-axis, symmetrically about the y-axis, then the terminal point for 2 pi over 3, all you do is you retain the ordinate, but you negate the abscissa. So that would be negative 1/2 square root of 3 over 2, okay, by symmetry. All right, so now, so the cosine of 2 pi over 3 is negative 1/2, and so the y-intercept then would be x equals 0, 3/4 times negative 1/2, which is negative 3/8. Okay, you see where I got negative 3/8 is? I multiplied 3/4, the amplitude, by the cosine. You have two numbers you're multiplying here, and so 0, negative 3/8. So let's check. Is that right? Yeah. So that would be the coordinate of this y-intercept, which is the midpoint of this line segment right there. Okay. All right. So there we go. So we can glean a lot of information from trigonometric functions. We've got the amplitude, we have the intercepts, we have the period, phase shift. Now, if you were to graph this function over several periods, easily done. All you do is you just take the set of points which make up the blue curve, copy it, and start pasting it at the end of the period. So just take the blue curve, copy, paste, paste, paste. Okay, or you can start at negative pi thirds and paste to the left. Okay, but the tricky part is making sure that the intercepts are correct and that the local mins and local maxes are correct. So that's something we'll explore more. And this is done with all 6 trig functions. This is the same technique we'll use with all 6 trigonometric functions. Okay, so I want to give you a summary sketch, summarize what we've done so far with graphing of trigonometric functions. Let me pull up the note. So if we were to take a trig function, say a sine or cosine function, or any trig function for that matter, and we gave it an amplitude, a period, modified its period, and gave it a phase shift, the only thing that remains to be done now would be to give it a vertical shift. All right, and so if we give it a vertical shift, I guess the question would be, what would be its new amplitude? Would that affect the amplitude? So let me show you what I mean. Let me show you what I mean. So a generalized figure here. All right, so let's consider this blue curve, which is the graph of a generalized sine function, and it's y is equal to a sine of k times t minus b plus c. So what's going on here? Well, okay, what we've graphed prior was essentially c equals 0. So now when you add this constant, the period is still 2 pi over k is your period. Okay, and that's stated here. Okay, the phase shift. Okay, so what is the phase shift? The phase shift is still b after you factor k out. All right, so adding this constant doesn't impact the phase shift. We're shifting to the right b units, and that's reflected right here in the coordinates of the endpoints of the interval of the period. But note that we have to shift the blue curve up c units. Okay, the amplitude still remains the same. The amplitude is still a. So shifting a curve vertically does not modify the amplitude. And so here's the line y equals c. But what we get then is that c is considered to be what's called the average value of the function. Right? The average value. An average value is just like any other average. You add up all the numbers and divide by the count of the numbers. But in this case, we have an infinite number of points on the blue curve. So the way we discern the average value of the function here is that we have an equal number of points above the c-axis, and then a positive value, and then the same output values are negated below the x-axis, so the average essentially becomes 0. But since we shifted it up, the average becomes c. Okay, all right. So that's the average value. So you may be asked, what is the average value of the function? The local maximum, of course, changes. The local maximum is now has an ordinate of c plus the phase shift, the absolute value of a. And the local minimum, the ordinate of the local minimum, of course, changes to c minus the absolute value of a. Okay, so shifting a curve up or down vertically has no impact on the amplitude, phase shift, or period. Okay, the amplitude is still the multiplier on the trig function, irrespective of how you shift it. So don't forget that technical point. All right. Now shifting it up, of course, does change the presence of x-intercepts. So in this case, when we shifted it up, this particular curve up, we lost all of our x-intercepts. Okay, and if we were to extend this function periodically, we'll still have a y-intercept, but its value will change because you will add c to the ordinate of the original y-intercept. Okay, all right. So let's do some examples. All right. So I have a sequence of graphs I'd like to show you. I think we have all the theory now to graph sines and cosine functions, and like I said, we'll get to the other 4 as soon as we become more proficient in these. Let me check to see if they're, yeah. So we'll just confine our graphing structures to sine and cosine. All right. So let me insert a internet browser, and we'll go back to our graphing tool. All right, and the first function we want to explore would be, let's erase that. I'm going to get rid of the keyboard so I can write. And let me change my window properties to display in radians and x-axis labels in terms of pi. All right, so we're in radian mode with pi, multiples of pi on the t-axis or x-axis. All right, so let's discuss the graph y is equal to 3 plus 3 sine x. So the first thing we want to do is to sketch this graph is the first thing is we want to sketch the graph of y equals sine x to get perspective. So y is equal to sine x. Okay. And then I lost my window settings again. Come on, radians, please. All right. I don't know why it keeps flipping back to degrees. All right. So the red curve is y equals sine x. So you'll draw that first using the techniques from at the start of this lecture. The next thing you want to do is you want to do a vertical stretch. Okay. And so to do a vertical stretch, what I would suggest doing is identifying all the intercepts, okay, right here, and just taking the outputs at all the intercepts. Well, the outputs are at all the x-intercepts would still be 0, so there's no vertical stretching going on at the intercepts. But at the, say at the local maximum, okay, so this local maximum right here is 1, and that will happen at pi halves. So you can verify that. I guess I have to zoom in. All right, so let's zoom in a bit. So at pi halves, that's the local maximum. So with the vertical stretch, just take the output at pi halves and multiply it by 3. All right, so pi halves 3 would be now here. All right, so right there. And this is where you really need to have some good trigonometric graph paper. And there's some on the class website that you can print out. All right, and then you'll do the same for the local max here. Right, and then you'll do the same for the local min. So this is, if you identify the local min, it should be negative pi halves negative 1. Right there. So there's your local min. And so we take negative 1 and we multiply it by 3. Okay, so and so that will produce a point right here. Okay, all right. So and then we'll do the same for this local min. We'll just do it over on this interval. So right there. Okay, so we have these 4 points that are going to be on our stretch sine wave. So let me erase that. Okay. Perhaps I should change color so they won't be confused. So we're going to connect the dots here. We're going to connect the dots here. Connect the dot here, 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 and here to accomplish the vertical stretch. So we would anticipate that this would be 3 sine x, like this. Okay, so draw the sinusoidal curve. Like this. All right? Okay, so that's 3 sine x, shown in blue. That would be the next thing you would do. And then finally, to finish the graph, you just take the blue curve and you shift it up 3 units. So, and do the same thing. So in this case, 3 would be shifted to 6, okay? This x-intercept would be shifted up 3 units, so that would move up to 3. And this 3 would be moved up to 0. This 0 would be, the output 0 here would be moved up to 3. The output here would be moved up to 6, but it's beyond the scale. And the output here would be moved up to 3. And the output here would be moved up to 0, right here. Right, and so we can connect the green dots to get the final graph. So it would look something like Okay, so it would go off the graph and then come back down. So I'll have to zoom. I'll have to zoom out to get the correct readings, okay? And so that's how you would sketch it. You would sketch it in that order: red, blue, green, okay? So we can check our answer using the computer. So let me erase, because I'm going to change the scales, and the overlay drawings won't look correct. So first we deal with y is equal to 3 sine x. And that's shown in blue. Okay, so there, as promised, there's your vertical stretch. All right, and then we just take the blue curve and we add 3 to it. So y is equal to 3 sine x plus 3. And so your answer is shown in green. So note that this curve will never fall, the green curve will never fall below the x-axis. It'll touch the x-axis at the intercepts, but it'll never fall below. All right, so that's how that works. All right. Okay, and so 3 cosine x was the next one. I think we've done that. Y equals -2 plus cosine x. That's just a vertical shift of the curve down. Negative sine x. Okay, we've done that one. Okay, oh, here's an interesting one. How about the absolute value of the sine function? All right, so let me take away this. Okay, so, all right, so, and let's zoom out. I think we may have done this. I'm not sure. All right, so the red curve is the sine function. Now, so if we were to take the absolute value of this red curve, the sine function, absolute value means that we can have nothing below the t-axis. So all of these parts that you're seeing below the t-axis, right here, this part, see, we have some negative stuff here. So in taking the absolute value is going to take the negative stuff and it's going to reflect it about the t-axis like that. Okay, so we have to flip the negative stuff above the t-axis. Right? So that's what we would expect the absolute value of the sine function to look like. And so let's do that. So y is equal to absolute value of sine of x. Okay, and let's see the graph. And there it is. Okay, I think we may have done that. Okay. All right. So let's talk about the graph of y equals negative sine 2x. Okay, so let me delete this. So the work to be done here is y is equal to negative sine of 2x. Okay, so this would be an example of a reflection about the t-axis combined with a horizontal shrink. Okay, so we're going to compress the sine wave. And as you know, the period of this sine wave would be 2 pi over k, k being 2, so that would be pi. Right? All right, so the way you would proceed with this is you'll start off with the graph of the sine function. So y is equal to sine x, shown in orange now. Okay, and now the first thing I would recommend would be to do what's inside of parentheses first, as is usually the case with mathematics. Do the operator inside of parentheses first. Okay, so this is y is equal to negative sine 2x. So that means what we have to do is we have to compress the curve. So how do we compress? Okay, so that means the period is now pi, so we have to take the period right here, shown and accentuated in red. This will be our new period, and we have to divide it into 4 equal subintervals. Because why is that? Because here's why. On the standard interval, 0 to 2 pi for a sine function, we have 4 reference points that are easy to plot. Okay, the reference points would be these three x-intercepts and this local max and this local min. Okay, so that's 1, 2, 3, 4, 5. Okay, so basically we have an output here that's easy to know, an output here that's easy to know, an output here that's easy to know. So 1 interval, 2 intervals, 3 intervals, 4 intervals, subintervals along the period. Okay, so always take the interval of periodicity, in this case 0 to 2 pi, and divide it into 4 equal parts for ease of graphing. So that means what we'll do is we'll take pi and we'll divide it into 4 equal parts. Okay, so pi halves is the midpoint, and then we take the left interval, so this would be pi fourths. Okay, this would be pi halves, and then the midpoint here of this right subinterval would be 3 pi over 4. So that's the strategy. Divide the interval into 4, the interval of the period into 4 equally length subintervals like this. Now, okay, so you know that for the sine function, at the midpoint of the period, 0 to 2 pi, the output is 0. So that means in this case, the midpoint of the modified period is pi halves, and so the output would be 0 as well. Okay, and so the output at pi would be 0. Okay, because that's the last endpoint of the modified period. And let's see what else. Okay, so we know that at pi halves, on the original sine function, the output was 1. Okay, so now by the process of the horizontal shrink, okay, pi halves occurred at the midpoint between 0 and halfway through the period. Okay, so now at pi fourths, then we would have 1 by the horizontal shrinking translation process. Okay, because you know the maximal value occurs at the midpoint of halfway through the period. Okay, the midpoint right here, pi fourths, is halfway through the period. The interval which is defined as half of the period. Okay, so that's kind of the translation. And then 0 stays the same, and then at 3 pi over 4, well, that's the midpoint of the other half of the period, and so the midpoint of the right half of the period, okay, at that midpoint, the output is -1. So we'll make this a -1 right here. Right, so that would be that's how you could analyze the horizontal shrink. And so therefore, if you connect the dots, it'll look like this. Okay, so you see how it, at least on one period. Okay, see how it shrank. Now I may ask you to say, okay, extend the graph for another period. So in this case, say go to pi halves here, have it, have the interval, have the interval. Okay, and since the sine function is odd symmetric, we know we have to come down to -1 here. We have to come up back to 0 here by odd symmetry, and then we come back like this. So there is a sine of 2x sketched on 2 periods. And then of course you can come back down like that if you want, okay, and continue on and on and on. So that's how you would. So if you have knowledge of the local min, local max, and the x-intercepts, you can take advantage of that to make the determination of where the local mins and local maxes and the x-intercepts of the horizontally shrunk curve would be. Right. So that's sine 2x. Now, so the question asks for the negative of sine 2x. So easily enough, right? We just take the curve and we reflect it about the t-axis. So we'll have this. So here's one period like this. So the blue curve is the answer, like that, and then reflect about the t-axis. like this. Okay, and so there's your curve, all right? And we can validate that by actually plugging it in and checking with the computer. All right, so we would have y is equal to negative sine of 2x. And we'll check. Okay, and that's shown in I guess it's shown in black, right? So let's see. Let me erase the content. Is that right? Negative sine of 2x, 2 pi. The period should be pi. Oh, that's the black curve. I'm sorry, that's the black curve. Yeah, the period is pi. Yeah, correct. And then you have the reflection. Yeah, so that is correct. Yeah, just as we said. You see the period is pi. Okay, pi, and it's a reflection. Okay, so negative sine 2x. All right, this is an interesting one. The next curve now the multiplier on x to modify the period doesn't always have to be an integer. So let's look at that. All right, so I want to sketch the graph of y is equal to negative 2 sine of 2 pi x. Okay, so this is just like the previous problem, except now our period would be 2 pi over 2 pi, which is equal to 1. Okay, so that's be a little bit different. So that's what you would sketch first. So where is so actually I need to adjust my window if it'll let me, and we need to go back to flip back to using x-axis labels with integers. Okay. All right. So start off by sketching the sine function with period of 1. So sine of 0, of course, is 0. So let's do this in green. And we have a period of 1. Like there's 1. And so we take 1 and we divide it into 4 subintervals, like this. Okay, and so the sine at the midway through the period is 0. And the sine at halfway through the left period, I'll call this the left period, is 1. So we would have a 1 midway through the left period, which would be here. And the sine of midway through the right period, which I'll call the interval from a half to 1, would be negative 1. So it would look like this. So there's your compression right there. So this would be the sine of 2 pi x from 0 to 1. And then all we do is we take the green curve and reflect it about the t-axis. So that would look something like this. Let's see, we start at 0. We go to negative 1. Come back, go up, and do that. Okay, so there you have it. All right, so now, for test questions, if this were a paper-based test, this is how I would ask that you would sketch the graph. You would show these intermediate steps. You would start off by sketching y equals sine x, then you would sketch y equals sine 2 pi x, and then you would reflect it. In this case, I used negative 1. Actually, I should have used negative 2. So, and then you would sketch the vertical stretch. So the purple curve is actually the correct answer. because it's a negative 2. So the graph will look something like that. I guess what's interesting is that the x-axis is rescaled. It's no longer in terms of pi. Okay, so we can verify that using the computer. Right, so the first one was y is equal to sine of 2 pi x. Okay, and that's shown in red. Okay, so you can see one period ranges from 0 to 1, and that's what we did. And then, so now we need to multiply it by 2 to stretch it. Okay, and there's the positive stretch, and then we need to reflect it about the t-axis or the x-axis. Okay, and so there's the reflection. So that's what your graph should look like. All right. Okay. So next graph, let's get rid of this one. Let's combine all of the operations. So how about, except without a vertical shift. All right, I won't do a vertical shift. So y is equal to -4 sine of 2. I'll go ahead and factor this for you, of x plus pi halves. Okay, so in this case, the solution would, the way I would proceed solving this would, I would first note that the period is 2 pi over 2, which is pi. So my period is going to be pi. So I've got to adjust my window now back to radian. So it's already in radians, but I need to adjust the x-axis labels in terms of pi for ease of sketching. Okay, and so my period is pi, so we'll sketch the graph of y equals sine x with a period of pi, or that is y equals sine 2x. So we'll start off with graphing the sketch y equals sine 2x. Okay, so that means the period is pi, so here's pi halves, pi fourths, 3 pi over 4. And so my output midway through the period should be 0. At 3 pi over 4, we should have an output of -1, which is right here. And the output at pi fourths should be 1, which is right here. And the 0.00 is still in the curve. So the purple graph let's see, is that right? Let's see, if pi halves. Yeah, and then at pi, we come back to 0. Okay, so there's one period of y equals sine 2x. So this is y is equal to sine 2x. All right, and then we have to shift the purple curve to the left, pi halves radians. Okay, so we'll do that in blue. So here's pi halves. Okay, and so we take 0, this point right here, we'll go here, and pi fourths. So this is pi fourths, so pi fourths minus pi halves is negative pi fourths, right? So that would put us here. So we would have an output here. This is pi halves, so we come back to 0. 3/4 pi, the output at 3/4 pi now gets shifted to what? Pi fourths, okay? And so the output would be here, and then the output at pi gets shifted to pi halves. So So the shifted curve, the left shifted curve would look like this over one period. Okay, like that. And then what do we do next? Okay, so we have to multiply the output by -4. All right, so we'll do that in green. So this point stays the same. This is -1, so -1. No, I'm sorry, this is +1. So +1 times a -4 would come down to here. So at -π4, the output is -4. At 0, the output stays the same. At π4, let's see, the output is -1 times -4. So at π4, we have to go to 4. And then the x-intercept stays the same with an amplitude modification. So our graph will look something like this over one period. Like that. Okay. So this is how you would step through the graphing of these functions. It's a lot more interesting than trig functions than with algebraic functions when it comes to function transformations. All right. Okay. Okay, so let's do one more trig function, a modified trig function. So let me erase all of this. And let's sketch the graph of y is equal to this. Let me write it out. So y is equal to 2 times the sine of x minus π3. Okay, so the first thing you want to do in sketching this function is you simply want to take the sine function and shift it to the right π3 radians. So perhaps if I zoomed in. Okay, so there we go. So let's do that. So here's the sine function, and we want to take it and shift it. So the output 0, so the green curve will be a shift, a right shift. So we have this point. So at pi halves, right here the output is 1. So now we have to add π3 to pi halves. So what is π3 plus pi halves? That would be 5 pi over 6, right? So that would occur roughly 5 pi over 6 would be just shy of pi. Let's see, this would be 4 pi over 6. So that would be roughly midway right here. So here's 5 pi over 6 right there. Okay, so we would have an output of 1 here. So the output at pi gets shifted over here. Okay, and so, all right, and so I'm out of space on the right, so I'll go to the left. Okay, so the output right here is at, so let's see, where does this peak value occur at? So this is negative pi halves right here, so we would have to add π3 to negative pi halves. So that would be what, negative 3 pi over 6. So we would have to shift this output to negative pi over 6. So all right, let's check. Okay, so we have negative pi halves. The output at negative pi halves is -1. And then we shift it to the right π3. So what is this? So that's equal to -3/6 plus 2/6. That's negative pi 6. So this output right here gets shifted to negative pi 6, which is halfway between here. So at this point, okay, so at this value of t, we would have an output of negative 1. So that point gets shifted there. All right. Okay, and so we have this. Is that it? Is that all we need? So we have this point. 1, 2. Yeah, so I think that's all we need. Oh, I guess, and then we could start it. We could plot this x-intercept right here. See this point right here, negative pi. Okay, that gets shifted to the right pi thirds. So yeah, so there we have it. All right, so the right shift of sine by pi thirds radians would go like this. Okay. Like that, okay. And then all we do is a vertical stretch by 2 units. So this would go down to negative 2 right here. Just multiply the outputs by negative 2. And this would go up to 2 right here. All right, so for one period, the graph would look like this. Let's see. Actually, this is greater than 1 period, right? Or less than. Okay. Okay, so you would have something like that, and you would complete it. So where would the next intercept be? So the next intercept would be at, wait a minute, let's see. So we go in here. So we've got to go back to 0 to complete the period. So 4 pi over 3 plus pi over 3 is pi. So that would be roughly here. So we got to come back to, yeah, we got to come back to, let's see. Oh yeah, we got to come back down like that. No, we got to do that. Okay, yeah, because we have to multiply all the outputs by 2. Okay, let me check if that's the right answer. Yes, that is the right answer. Okay, so there's one period of y equals 2 sine times x minus 3. And it's shown in blue. Okay, so that's how that works. All right. So don't forget, if there were a multiplier, I didn't do too many examples, but if we had something like, say y is equal to 2 times sine of 3x plus pi halves. Okay? Don't forget, if I ask you to graph this, that you would have to factor the 3 out so that you can get your periodicity. So you would have to factor 3 out of the first 2 terms in parentheses, and your graph would look like this. Okay, so you would graph a graph with period of 2 pi over 3, and it would be left shifted pi 6, left shift pi 6. So period is 2 pi over 3. And the phase shift, B, is equal to negative pi 6. So actually what you would do is you would shift this graph. This graph would be left shifted pi 6. You'd shift it to the left pi 6, and the phase shift would be negative pi 6. Okay? A left shift of a graph means a negative phase shift. Okay, so don't forget those ideas. And then you would graph it just the way we did this exercise. Okay. All right. Now, something interesting. What if we were to multiply a trigonometric function by an algebraic function? How would we sketch its graph? All right, so whoops, what happened? Let's go back. So special things happen when we combine our algebra functions with our trig functions in a multiplying arrangement. So let's do this. Erase everything we've done. So I'll give you a quick procedure for doing that. It's kind of an interesting, rather peculiar procedure. So suppose I ask you to graph y is equal to cosine of 2 pi x divided by 1 plus x squared. All right, so I'll give you the procedure for doing this. The first thing you want to do is you want to process the algebraic part first, right? And the way you process the algebraic part is you identify that the algebraic part is y equals 1 divided by 1 plus x squared. So using your techniques from the first lecture, okay, just go ahead and graph this. Okay, and that's shown in red, hopefully. Okay, so there it is shown in red. Y equals 1 plus x squared. Then the next thing you want to do, and this is where it gets interesting, is you want to next sketch the graph of the negative of the algebraic component. So you want to sketch the graph of this. All right, and that'll be shown in blue. Okay, so what we have here is we've got what's called the envelope. Okay, so the cosine 2 pi x will be drawn within this envelope. Okay, so now all you have to do is just sketch cosine 2 pi x so that it doesn't go outside. So here's how you would do it. So I'll do it in green, and this will be actually the graph of y for y. So at x equals 0, cosine of 2 pi x is 1, and cosine of 2 pi x has a period of 1. Okay, so so first of all, identify the period of 1, and then slice it into 4 equal subintervals, like so. And so we know that the cosine function, let's see, at 1/4 of the way through its, oops, sorry, I have too many dots there, don't I? I didn't do that right. So where is 1? 1, 1, 2, 3, 4. So 1 is right here. There's 1. And so we know that the cosine function halfway through its left period, which I call this the left period, would be 0. And then at the end point of its left period, the output would be, oh, let's see, the cosine, excuse me, the cosine, yeah. The output would be -1. So, but notice that the cosine function will not go to -1. Here's -1 right here. The cosine function will go until it touches the bottom part of the envelope. So it'll never reach a value of -1 because it's blocked by the bottom envelope. Right? And then we know the cosine function halfway through its right period, okay, I call this the right period, will go to 0, and then at the end of its period, the cosine function should attain a value of 1. But in this case, as we journey toward 1, we're blocked by the red curve. And so we stop where the red curve blocks us. And then we just repeat. We just repeat. So it's gonna go and it's just going to keep touching the curve like this, right? So essentially what we have defined is an asymptote for this graph. So the algebraic part actually becomes an asymptote, interesting enough. So a very strange asymptote. So to show you, to convince you this is correct, I'll go ahead and let the computer complete the graph. So let me erase the green portion and go ahead and show you the remaining part. So this would be y is equal to cosine of 2 pi x divided by 1 plus x squared. And there you see how the green part is confined to the envelope, where the x-intercepts of the green curve are still the same as the x-intercepts of y equals cosine 2 pi x, but the amplitude is chopped. It's blocked by the boundary of the envelope. All right, so that's kind of interesting. Okay. This is called a carrier wave. This is how radio stations work, are used to. This is the carrier wave. See, the signal, the green part is called a signal, which is received by a cell phone or a radio, and the red and blue curves are called the envelope. And so that's how radio transmission works. You take your information and you embed it in an envelope, and then you transmit the envelope with the information. And then your receiver basically matches the envelope and peels it back to pull out the information. And that's all done electronically. So if you're in electrical engineering, get used to this. Okay. Okay, and just as another example, we can do y equals, say, x cosine x. I'll explain that to you. And I think this will be the last part of the sine and cosine, discussions of the sine and cosine functions. Yeah, so one more example. How about we consider the graph of y is equal to x times cosine of x. And that's shown in purple. All right. So the way this curve was derived looks kind of strange, doesn't it? What we did was we drew the envelope by first graphing y equals x, which is shown in orange, and then we completed the envelope by graphing y equals minus x, which is shown in black. Okay, so now let's see what the results are. Okay, so the black and the orange curves define our envelope, and then we confine our sketch of the cosine function. Let me change the yeah, we can leave it like that. We confine our cosine function so that it's cosinusoidal, but it touches the boundaries of the envelope. So maybe if I were to adjust the x-axis so that it's represented, the labels are in terms of pi. Okay, there you can see the purple curve is still the cosine function, but now the effect of the multiplier on x is to induce a vertical stretch or a vertical shrink depending on where you're at. The period of the cosine function remains the same, 0 to 2 pi, but the amplitude is now modified by the envelope. So this is an amplitude modulation process going on here. So this is x cosine x. Yeah. All right. Okay, so that's it for sine and cosine. So the next lecture topic will deal with the rational trig functions. That would be tan, cotangent, tangent, cotangent, cosecant, and secant. So we'll discuss how to graph those functions. And you can kind of anticipate, since they're all rational functions, they're going to have vertical asymptotes. All right, so that's it for this lecture.